Thank you very much. I like to first thank the organizers for giving me this opportunity. So, without further ado, I will start my talk. And the title of my talk is The Prospect of Distinguishing Stellar Mass Compact Objects in Extremal Mass Ratio Inspiral System with LISA observations. So, this work is based on this talk is based on this work, and which I have done with in collaboration with Professor Arpan Bhattacharya. So previously, there have been some interesting talks about extremal mass ratio system in this seminar. In particular, Shayab Dotto, Beatrice Bonga, Michel Levy, and yesterday Adam Pound pointed out some scientific potential of such system. And in any way, I will just first give a brief introduction about the extremal mass ratio system. So extremal mass ratio system, or the EMRIs, are a binary system where a stellar mass compact object orbits around a supermassive compact object. For brevity, from now on, I will call the supermassive object as the primary object of the EMRI system and the stellar mass object as the secondary object of our system. The mass ratio of such system is quite small, ranging between 10 to the power minus 4 to 10 to the power minus 7. And as Shayab Dotto previously pointed out, the secondary object spent from few months to few years inspiraling around the primary object, and in this process, it emits gravitational wave in millihertz frequency range. And as you know that LISA is most sensitive in this frequency range, so this makes the EMRI system a prime target for LISA observations. Now, the EMRI waveforms, gravitational waveform from EMRI system carries very detailed information about the physical parameters of the binary system, like its mass, the mass and angular momentum of the primary, also the nature of the primary object, and also the space-time geometry around the primary object too. So in this talk, I am mainly focusing on the following question: that whether it is possible to identify the nature of the secondary object in the EMRI system with LISA observations. In other words, we want to check whether the secondary object is a black hole or a neutron star or some other exact object like boson star, etc. So first, I will model our EMRI system. So we consider that the primary object of our system is a supermassive Kerr black hole. And for secondary, we take it as an extended object which is spinning, and due to its spin, it induces quadrupolar deformation. Now, dynamics of such system can be done by Dixon's multipolar expansion method. And the dynamics of such system can be well described by multipolar expansion method, which put forwarded by Dixon. And the basic underlying idea about such multipolar expansion is that the information about the internal structure of the secondary is thought to be encoded in a set of multipolar moments, and this set is usually infinite. But for EMRI system, where Q is the mass ratio is quite small, and for this scenario, we will only need a finite amount of multiple moment terms in order to describe the dynamics. In this case, for our situation, we consider the energy momentum tensor of the secondary object as given by this equation, where P is the momentum of the object, V is the tangent to a reference word line, S mu nu is the spin tensor, and J mu nu alpha beta is quadrupolar moment. Now, as you can see from this equation, if you just take the first bracket term here, it is only pointing out that it is a stress energy tensor for a point particle. When we consider also the spin effect, then it describes a extended spinning object. And if we consider the quadrupolar momentum, it will describe a spinning object that is subject to a quadrupolar deformation. Now, from covariant conservation equation of energy momentum tensor, we can find the equation of motion of the secondary, which is given by the Matheson-Pavlovich-Dixon equation, and this equation is given in here. Now, the physical meaning of such equation is that the total force and the total torque on the system is zero. Now, it is quite well known that this MPD equation or Matheson-Pavlovich-Dixon equation is a underdetermined set of equations because the number of parameters exceeds that the number of equation. So this scenario we have to give some supplementary condition in order to study the dynamics of such systems, where we choose to spin supplementary condition. The basic idea behind this thing is that by choosing such supplementary condition, we choose a reference word line with respect to which we calculate the moments of the calculate the multipolar moments. Now, another unknown about system is the quadrupolar tensor, and as I said before, we are looking for a scenario that the quadrupolar deformation is induced only by the spin effects. And in this scenario, the quadrupolar moment can be written in this following fashion, where mu square is the dynamical rest mass of the system, and q alpha beta is the mass quadrupolar tensor, which is a quadratic function of the spin tensor. Here, CQ is a dimensional parameter that accounts for the quadrupolar deformation due to spin effects. From now on, I will call it spin-induced quadrupolar moment moment parameter, or SIQM parameter. And this parameter is closely related to Wilson parameter that a few days ago Professor Michel Levy talked about. And this parameter takes different value for different astrophysical objects. For a black hole, it takes the value 1 in accordance to the Noether theorem. For a neutron star, it ranges between 3 to 20, depending on the equation state of the neutron star. And for boson star, it can be quite large. It ranges between 10 to 150. And interestingly enough, there are other situations where in Bravo star case, it can also take negative values. Now, before moving any further, let me give a order of estimated order of magnitude analysis to check whether such quadrupolar deformation terms can actually have an imprint on the dynamics of the object. So we consider that the secondary object as a perturbation to the space-time geometry of the primary object. So the part-up metric can be written in this following fashion, where the bar g mu nu is the background car geometry, and h mu nu h1 and h2 denotes the first and second order perturbations. Now, this perturbation accelerates the secondary away from its trajectory and drives the object in an inspiral phase. So the covariant acceleration equation then can be written in this following fashion, where f1 and f2 are the force terms, first and second order force terms, and those can be due to self force or finite size effect, as we are considering here now. So in this f2 term, the effect of quadrupolar deformation, information about quadrupolar deformation is encoded, and we want to check whether during this inspiral period this term can have a actually significant effect on orbital dynamics or not. So as you can see that the inspiral time scale is quite large for a MRI system. It is proportional to m by q, where m is the mass of the primary object and q is the mass ratio. So which is quite large. Then over the inspiral period, this second order force term produces a shift in the orbital dynamics that is of the order of q naught. So from this thing, we can say that we cannot neglect the effect of second order force terms like quadrupolar deformation. This analysis also provides a understanding about whether we need to consider higher order force terms or not. If you take another term, say q cube and third order fourth term, then this shift is of the order of q inverse. With this analysis in our mind, we can safely say that quadrupolar deformation can have a significant effect on the dynamics of the EMRA system. And moving forward, we next find the conserved quantity of our MPD system, and due to the as we are considering a curved black hole, background curved black hole, the conserved quantities are the energy and angular momentum. And furthermore, it is quite well known that in presence of a quadrupolar deformation, the dynamical mass time is not conserved, but we can actually construct a mass-like quantity, which we call the renormalized mass term, which is actually conserved up to order q square.
So, so as I said before, that we have two time scale associated with the system. So we can think that in smaller time scale, which smaller time scale, we can think the motion of the motion of this secondary object, that motion of the secondary object as if it is moving on its trajectory, and we can thought the inspiral period as a flow from one circular orbit to another other circular orbit, and the flow rate is determined by the rate of change of energy and angular momentum. And in adiabatic approximation, we will need only consider the time average part of the cell force, where here Ck is the energy and angular momentum. Now, in order to find the average rate at which the secondary object emits gravitational wave, we need to solve the Tucholsky equation. Now, the information about the gravitational degrees of freedom is encoded in the Weyl scalar, and for a curved black hole, that can be separable as follows, where S is the spin-weighted spiral harmonics, and R is the R satisfies the radial Tucholsky equation with a source term. This source term depends on two things: the choice of our energy momentum tensor for the secondary, and the second is it depends also on the eigen values of the spiral angular Tucholsky equation. So we solve this radial Tucholsky equation within the framework of green function method. So one important ingredient to solve this equation is to find the solution of homogeneous Tucholsky equation. And we find this homogeneous Tucholsky equation by using black hole perturbation toolkit package. Here the solutions are R in and R out. They are where R in is a wave that is incoming from the past null infinity, and R up is a wave that is incoming from the right past horizon. Now, with this information about R in and R up, we can then calculate the gravitational wave flux at some specific radius R naught, and which can be represented in this following fashion. Where Carly M is given by this equation, where A0, A1, A2, A3, and A4 depends on the stress energy tensor of the secondary, and also on the eigenfunction of the angular Tucholsky equation. And we can get the total flux by adding the flux emitted to infinity and the flux emitted to the event horizon. And with this in our hand, we can then calculate the adiabatic evolution of orbital radius and the phase of this secondary. And this can be solved by solving this equation. We solve this equation by using numerical methods, and from which we can find the phase of the gravitational wave by this following relation, where we only consider the dominant consider the dominant mode. Now the result is shown in here. So here the dashed line, here we plot the orbital radius and the phase in R5 plane, and here the dashed line represents the position of the ISCO, and we start our inspiral at r is equal to 10 m, and the inspiral stops when this secondary object reaches the ISCO position. And previously, as Shaib Datta pointed out, it will actually take almost 1 year of time to reach this ISCO position for this choice of parameters. And here we also plot the gravitational wave flux for different values of orbital radius. And as you can see from here, the flux increases as the secondary object approaches this ISCO position. Now, in order to understand the effect of quadrupolar deformation, we fit the numerical result for phase with a series of specific angular momentum of the secondary object. Here, the phi naught represents the phase for a non-spinning secondary object, and phi 1 and phi 2 delta phi 2 represents the correction terms that arises due to spin and quadrupolar deformation respectively. So first, this first plot is we are plotting phi 1, the first order the correction term that arises due to the spin effect only, and we plot it as a function of time for different values of CQ parameter. And as we expected that this CQ does not, we intuitionally you can think that CQ parameter does not have any impact on this phi 1 parameter, and this exactly shown in this plot. But this phi 1 parameter depends on the specific angular momentum of the primary object, and as you can see that as we increase the spin of the primary object, the inspiral time increases dramatically. In order to consider the second term, the term that arises due to the quadrupolar deformation, we put the following answers that this delta phi 2 has a linear dependence on CQ. CQ, and if this is true, then we expect that this phi 2 term does not have any effect on, does not depend on this CQ parameter. And this exactly shown in here. We have calculated it for different values of CQ for which are respectively 1, 10, and 100. And as you can see that the phi 2 parameter does not depend on this CQ value. But it also depends here also it depends on the specific angular momentum of the primary object, and it ranges between 1 to 10 as we increase for different values of specific angular momentum. As we increase the value of specific angular momentum of the primary, the value of phi 2 increases, as you can see from this plot. So we can then calculate the total accumulated phase in this following fashion, and we can also then calculate the shift in the orbital phase that is caused by quadrupolar deformation, which takes a remarkably simple form. Here, this phi 2, as shown before, is a numerical parameter that ranges between 1 to 10, and 10 for different values of specific angular values of angular momentum of the primary object. Now we want to check whether this quadrupolar deformation term can have any significant impact or that is resolvable by Lisa or not. So here we take the following. We take two models. One model that has taken the effect of quadrupolar deformation, while the other is not. And the systematic error due to the inaccuracy of modeling then if this inaccuracy is less than the statistical error due to detector noise, then we cannot identify the signature of quadrupole deformation with Lisa observation. In other words, the phase shift is resolvable when it exceeds some critical value. And we have calculated if this shift due to quadrupole deformation is greater than 0.01 radian, then we can actually find the effect of quadrupole deformation. And here we show the plots whether it is possible to detect the quadrupole deformation or not. Here we have plotted a contour plot in the parameter space of CQ and the specific angular momentum of the secondary object. For CQ, we have taken values from 1 to 150 as it ranges between these values for black hole, neutron star, and boson stars. And for the chi, we have taken the values 0 to 10. Uh, yeah, the value of chi seems to be very extreme from the astrophysical perspective, but as you know that black holes are limited by chi less than equal to 1. So they are limited by the car bound, but there are certain pulsars that or certain white dwarfs actually that can have such dramatical values of the specific angular momentum. Now we can see from this plot that there exists a large parameter space for which the detection for which the signature of quadrupole deformation can be detected, uh, and this is the range of detection. And as we here the first plot is for primary spin 0.03, the second plot is 0.06, and the third is for 0.09. So as we increase the value of the primary spin, then we can see that the parameter space for which the detection is possible get increased. So we can actually hope to probe some certain astrophysical objects like boson stars, and also certain super spinner objects. By super spinner we mean the astrophysical objects that reaches the car bound. And these models are usually motivated from string theory, and also there are certain boson star models first provided by Ryan, which can also breach this car bound. Now, the takeaway message is that the effect of quadrupole deformation can be quite significant for some exotic compact objects like boson stars and super spinors. And Lisa can detect those objects if those objects really exist in nature. And the parameter space for detection increases with the increase of primary spin. This is quite significant as the supermassive black holes are thought to be have very large value of spin. So this can be a possibility to detect some of these astrophysical objects. And the future directions can be said as follows. We can here we have taken the equatorial and circular orbit assumptions. We can relax those assumptions by taking some eccentric orbit, etc. We can also consider the effect of tidal fields, and I think the most important effect to consider is the Self force effect, that we can in future will try to check. And as yesterday Adam Pound pointed out that including the effect of Self force, then we can actually do this analysis for comparable mass binaries. Then it will be a very interesting project to check whether such Self force calculation can actually predict predict the nature of the astrophysical objects. So thank you very much. This is
So this work is in collaboration with my supervisor here at IIT Gandhinagar, Arpan Bhattacharya, and that's the title. So we are going to explore a situation like eccentric binaries in this gravity theory. But before going so, that's the outline of my talk. We are going to first give a brief review of eccentric binaries in GR, and then we will be extending it to the Horndesk theory, and we will computing, and we will show, and I'll show that how to compute some fluxes there, and then we'll look into some decay rates and then conclude. Okay, let's start. So let's start with this GR case. So we know that this is the theory is GR, and this is the Einstein's equation with the matter part in it, and our Einstein tensor is written in this form. So if we can reconstruct it, the equation looks like this. So R mu nu, this is all we know. Okay, this is something we know. But suppose we induce a perturbation in this metric with a background and a small amplitude perturbation. It turns out that this equation turns into this. Okay, where we have expanded this Riemann tensors to the quadratic of H mu nu. Okay, now this T mu nu, this tau mu nu is basically the energy momentum tensor of the gravitational waves, and this T mu nu prime T delta is the part of the matter in a case. Okay, so let's concentrate on this because we will be exploring radiations from a binary system. Let's concentrate on this gravitational wave energy momentum tensor. So this is the tensor. It comes out of this is gauge invariant. And when this tensor comes around, we can calculate this flux coefficient and calculate the total flux over all angles. Okay. And it turns out that this total flux calculated will come up in this form of multiple moments. Okay. And this multiple moments looks something like this. So these are all standard results in GR. And if we consider that these eccentric binaries are slowly rotating, they are slowly moving, then we can approximate this MKL with this dipole moment by a moment of inertia tensor. So now since we have a moment of inertia tensor, we can actually take natural systems to it. In our case, it will be binaries, and compute this moment of inertia tensor. Okay. So to compute this moment of inertia tensor, we look into two binaries of masses m1 and m2, and their radial, they have a parameterization like this, orbit parameterization like this. So these are eccentric. So these are all orbit parameterization, and we know that when we take this into account, we can calculate. So these binaries are moving around and they are radiating. The change in energy, the energy flux of the system, which is decreasing, is given something by this. This is the leading order calculation in GR. And our angular momentum of the system goes in the form of this. Okay. And we can use this all to construct a chirp signal in this way. And this is the typical form of the chirp signal. And as R is decreasing, its amplitude is increasing. So this is all standard. But this is absolutely not the case. However, we see that after this chirp signal, there is an inspiral, phase, there is a merger phase, and there's a ring down phase, stuff like that. So of course, somewhere along the line, we are missing something and we need to improve on it. So that's why these talks by Luc Blanchet yesterday and several other speakers, that we use systems like, we use techniques like post-Newtonian theories and numerical relativity to construct such waveforms. So this is something that we are going to do. This is something that we are going to do in our gravity theory, which is Horndesk theory. So a bit about this theory. So it's a theory which is a scalar in it, and the scalar couples to matter. Okay, and it couples in a very general way. So this is a much more general scalar tensor theory. Also, it evades all possible instabilities that can happen in a classical system. And these instabilities are of Ostrogradski type. And also, if you have a scalar field, it has applications in cosmology, in explaining phenomena like inflation and stuff. Okay, so that's there are much more motivations, but this is as far as it can go. But suppose this is a Horndesk theory, and this theory comes with a Lagrangian. So this is the type of Lagrangian. So this is the action of the part, and the Lagrangians here look very complicated. Okay, so you have a G2 term, G3 term as a function of phi, has a kinetic term to it, and all of this. This is, so you can find these terms, all these terms in this paper, Kobayashi paper. Okay, so but there have been many works on this theory, and most of the works have actually been able to constrain terms of this theory, that they have actually indicated that we don't need all of these terms. And the most and if we take these things into account, this paper, Zumala Karika Escuga paper, they have actually shown what can be the most allowed terms given the constraints from the theory. So we can see that this L5 we can safely choose to be 0 because it gives you a causal behavior to the theory, and we can safely choose this G3 to not be a function of this kinetic terms. Okay, so this is the action. This is the action that we are going to go forward. So if we take this action and we take the matter sector to compute the matter momentum tensor, energy momentum tensor, we can do so by varying it with the metric itself. Then this is the matter momentum tensor. We can go further. We can go further and we can look into what can be a radiation behavior in this theory. So for radiation behavior in theory, we have a scalar field and we have a background tensor, and we have a tensor field G mu nu. We need to perturb these two. So we are perturbing this G mu nu in the background of a flat space-time metric, and we are perturbing the scalar field in background of a constant phi 0. Okay, so after perturbing these equations, it turns out that the equations of motion for the tensorial part, there will be a tensorial part, and the scalar part, it comes out something like this. Okay, so this is of course so you compute the equations of motion for the tensor part, and you compute the equations of motion for the scalar part, and then you do some and then you just rearrange it and compute them at Pn orders. So we start computing this Horndesk theory at 1 Pn order to know the full solution of the theory, to know the 1 Pn solution of the theory. So when we do this, our background matrix at 1 Pn near zone solutions turns out to be something like this. Okay. So this is our up to V over C whole square. Okay. So this is the post-Newtonian solution of the metric, and we are much now equipped with using these post-Newtonian solutions in our solution for scalar phi. Okay, how do we do it? So before proceeding further, so now we have a theory in which there is a scalar and there is a tensor to it. So the energy momentum tensor for the gravitational waves must have a gravitational counterpart, it's just like the GR part, and must have a scalar counterpart, right? So we need the solution for this scalar field. So to solve for this scalar field, it comes out in an equation like this, a massive Klein-Gordon equation, which has a Green's function of this form. This is a complicated Green's function. And we can go about to compute this Green's function, and we can give a solution for phi tilde. And the solution for, in order to get a solution for phi tilde, this S is defined as some trace of the energy momentum tensor. Okay. So this is the T mu nu, which we compute at 1 Pn order, and then let's set this M of S to 0, purely for calculational purposes. If we set this MS to 0, we can see that the phi tilde solution turns out to be something like this. Okay, so this M of L here, the multiple moment here is actually a 1 Pn corrected solution for phi tilde. And when we do this, the full solution, we are now much more equipped with a solution for phi to calculate the energy momentum tensor for the gravitational waves. Okay, so we start doing it. So for doing it, we find out that for the rate of energy change of the system, we have a gravitation counterpart and a scalar counterpart. The gravitational counterpart in the tensorial counterpart here basically is looks something like this. So it looks like GR. The coefficients are different over here. And the scalar counterpart looks something like this, because our energy momentum tensor is something del mu phi, and we have a contribution from T0R component of the matrix. And what you do, you put the solutions of phi tilde into this equation, and you can find that our rate of energy loss of the system of the scalar part looks something like this. So it includes the monopole part and the dipole, octopole contribution. So every possible combinations are there. Okay, and we can go along to calculate.
Sorry to interrupt. I mean, you have 2-3 more minutes.
Yeah, sure. So we calculate this in a rate of energy change here, and then we can go along the same line to calculate the rate of angular momentum loss rate, the angular momentum loss rate for this binary system in this theory as well. So it is something like this. Okay, again, it has all the parts, not only the quadrupole part, just like unlike the GR case. Okay, so now we have this E dot and L dot. If we have an E dot and L dot, then we can use, so we can restore, we can restore the Keplerian laws in this theory, and we can write down an n-body equation of motion in this theory, and we can define an effective gravitational constant here, and we can also write a binding energy for this theory. And when we do it, we can find by taking derivative on both sides, we can find a rate of change of major axis in the binary itself. And we see that this rate of change of energy of the major axis change in the binary has a negative sign at upfront. Okay, and the whole matter over here has positive parts to it. Of course, the other terms are all scalar corrections, are all scalar terms plus the Newtonian corrections. And this negative term over here is suppressed by the GR counterpart as C4. So we can see that it is some GR part plus something, which shows that the rate of change of major axis is faster compared to GR. Okay. Similarly, we can go along the same line to compute the eccentricity change of the orbit, and we can see that this is the same thing. Again, we can seek upon this conclusion that every term over here will have a positive effect on the GR plus term. So at the end of the day, it has a negative sign up front. So the eccentricity of the orbit again will decrease. So as the take home message is, the binaries are moving around and they're radiating energy. There is an angular momentum loss rate, and we can see there is a change in the major axis, and there's a change in the eccentricity of the orbit. Okay, so that's what as part of the orbital dynamics is concerned. Now, the thing that we will be doing in the future, so just like in GR where we can compute the change in energy, where we can change the energy and something like that and use it to construct a waveform for the theory, we can do so for this Horned-Escape gravity as well. And this is something that we are going to do in our future work, constructing a waveform analytically, if possible, to construct a waveform. And then what we can do is do some constraining and stuff to put more stringent bounds on the couplings and in the theory. So that's it. So thank you.
So I will discuss about the ring down of compact objects other than black holes. And essentially, we will see how we can test the nature of the astrophysical sources by looking at the ring down stage of a gravitational wave signal. And we will see in the case in which the remnant of coalescences is a horizonless alternative to black hole, how the ring down will change in the quasi-normal mode spectrum in the emission of gravitational wave echoes. And we will do some preliminary analysis to assess the detectability of these extra signatures. So essentially, as we have seen during this conference, so far we have detected 90 gravitational wave events from the coalescence of compact binaries. And in this talk, I will focus specifically on the ring down stage, in which the final remnant of a coalescence relaxates to an equilibrium solution. And the main question I would like to address is what is the nature of the remnants of the events we observed so far. And indeed, from the detection of the ring down, it is possible to infer the nature of the remnant by looking at the quasi-normal modes of the system. Essentially, the ring down stage is dominated by the characteristic frequencies of the remnant, the so-called quasi-normal modes, and they are complex frequencies. They describe how the remnant respond to a gravitational perturbation. And the ring down signal can be modeled as a sum of exponentially damped sinusoids, where the frequencies are related to the real part of the quasi-normal modes of the remnant, and the damping times are inversely proportional to the imaginary part of the quasi-normal modes of the remnant. So from a detection of the ring down, we can infer the characteristic frequencies of the remnant and understand its nature. So far, we have detected the fundamental quasi-normal mode in several gravitational wave events. And these observations are compatible with Kerr black holes as predicted by general relativity. However, if we would like to perform a test of the no-hair theorem, we will need to detect at least two quasi-normal modes. In this way, we could check if the remnant has extra degrees of freedom, or if it is just described by a mass and the spin as predicted by general relativity. And indeed, in the future, with next observations, and especially with next generation detectors, we will be able to distinguish between several models. And from a theoretical standpoint, there are several models of alternatives to black holes that are as compact as black holes, but they do not have an horizon and they do not have a curvature singularity. So these models come from some quantum gravity extensions of general relativity, or are conceived within general relativity, but with some dark matter or exotic fields. And among all the models, we can recall fuzzballs that come from string theory, or boson stars with some ultralight dark matter fields. And some of these models can mimic black holes in terms of electromagnetic observations, but they will have some characteristic smoking gun